So for the next section, we're going to look at some of the bits of the report and how to interpret your report and how different situations will appear on the report. So I've just received my RIQAS report. What is the first thing that I should do? So we want to look at the summary page, because that's where we get our overview of the whole sample and all of our analytes, and we can see if we have any performance issues for all the parameters. So we went through this with Stephen earlier, so we're just going to highlight quickly. So we've got anything that's bold and underlined means it failed its performance indicator, and the red triangle indicates we failed all three. So the first thing we want to look at is our parameters with the three triangles. So we've got our three performance indicators, and as we said, anything where you fail on it is bold and underlined, and we want to find our red triangles. So if all three performance fails, we have our red triangle, and those are the ones we want to investigate. In this instance, we want to look at GGT, potassium, and Triggs total. These are going to be the three parameters that we need to investigate for this particular sample. So if we look at these three, we're going to need to look and see, is it just this one sample? Is it a long-term issue that we have? But if we look at this particular sample, we can see, if we look at the three different performance indicators, GGT is the worst performing. It's got our SDI is greater than 2, our percentage deviation is out, and our target score, so 10 is the lowest target score that you can get. As Stephen said, the target score ranges from 10 to 120, which is your best performance. 10 is your worst performance. So anything here you can see 10 is the worst, 14 is the next, and 27 is the next. So on the report page here we can see, if we look at the running mean target scores, if it's a long-term issue or if it's just this particular sample. And here for these parameters you can actually see that the running mean target scores, these ones are in the 80s and this one's in the 90s. So it's not a long-term performance issue that we have. There's a particular issue with this particular sample for these parameters. So this is why the summary page is the best place to go to get your initial information on your particular sample, and then we can look at the individual report pages to see what's wrong. So if we look at the other things on this summary page, there are other parameters that have failed on some of the performance indicators, but here you can see the SDI for these ones is less than 2, so it's not highlighted and we don't have a red triangle, but there is a performance issue here. So again, these need to be checked and monitored to see why these have failed on these two performance indicators. So these are the three that are going to be our first priority, and then our next priority will be these other ones that are also bold and underlined. So as we said, the running mean target scores are good for giving you your long-term performance indication. So as Stephen said, it's the average of your last 10 samples. So again, the running mean SDI and percentage deviation, we need to just be careful. You can see here you have positives and negative values. And so these can average each other out and appear better than the actual performance might be. And we'll see that on some charts in a moment. So the running mean target score is the best one to look at to get a first glance indication of your long-term performance for the parameters. So which of the parameters on this summary page shows the best long-term performance to date? So we've just said we want to look at our running mean target score, because this is the one that's always a positive value and is going to give us our best indication. So we want to have a look down the list and see which of these values is the highest. And if I come back up to the top, it's alkaline phosphatase has the highest. So I've highlighted the 3 with the highest running mean target score. So alkaline phosphatase is the highest at 109. And then you can see amylase total and sodium both have a running mean target score of 101. So anything over 100 is deemed to be excellent performance. So these 3 parameters are running with excellent performance. You can see there's some other ones here at 97, there's 2 at 97, another one at 94. So overall, the performance of this lab is good. You can keep a look here, so you can see the lowest here is 50. So that's maybe an analyte that they're going to want to keep an eye on. So the performance has been okay for this particular sample. So maybe they had an issue in the past that they've now resolved. So they need to just keep monitoring this and make sure that this value keeps going up to monitor their long-term performances. So this is the percentage deviation by sample chart, and this is just to show you how the running mean target score can look, the running mean percentage deviation can look better than the overall performance. So here you can see the lab has some samples that have failed. So there's 2 here that have been greater than 10% under the mean for comparison, and 2 here that have been greater than 10% above the mean for comparison, which have averaged out in the running mean for this sample. So the running mean, if you just looked at that value on its own, your performance would appear to be very good. But actually, when you look at the individual performance for the samples, you can see there's quite an erratic performance. And there are a number of samples in which this lab has failed for these particular samples that are circled in green. So Stephen mentioned the red section is based on the percentage or the TDPA for the sample, in this instance at 6.3, and here you can see the line is sitting here at 6.3. So this is the lab's percentage deviation for the current sample is 8.9, which you can see is in the red zone, but the running mean is 3.4, which is much lower and is within the acceptable limits. But actually, when you look at the overall performance, it's not as good as the running mean might indicate. So the running mean does have benefits because it can help you look when all the results are either above and the lab's running with positive bias or below. It can be helpful for monitoring the level of the bias that you have across the different concentrations. But it's just to be aware that there are some drawbacks, and everything on the RIQAS report needs to not be taken in isolation, but looked at in conjunction with all the other different charts that are on the report. So this is a different sample page. So we can see this time there are only 2 analytes, have been flagged, urea and uric acid. So I'm just going to leave that there for about 5 seconds, just while I talk, before I hit the next. Move on. So what do you think could be wrong with this report? So everything else has performed well for this particular sample, but these 2 have failed. We're flagged for our 3 performance indicators, and we have the red triangle. So if you look at the mean for comparison and the lab's result, you can actually see they've put the urea result under uric acid and the uric acid result under urea. So they've actually mixed these 2 results up. And you can see that if they put the result in under the correct one, the performance would have been good. The lab's result was 10.8 compared to 10.2, and the lab's result for urea was 68.1 compared to 67.2. So actually, if the lab had not mixed them up, their performance would have been good and nothing would have been flagged. But because they've mixed them, we have our per performance flag. So the lab in this instance would be able to request that these results get corrected. So as long as they do that within 4 weeks of the final sample date, they can fill in the relevant paperwork, request the correction, and send a copy of the analyzer printout, and then these results will be corrected. And on the lab's next report, following the correction, they would see the improved performance for this particular. So these performance indicators would actually reflect the true performance of the lab once the result has been corrected. So this is another summary page, and as you can see this time we have a lot of red triangles. So this is what you don't want to see on your report whenever you turn to the summary page, because this means that there has been an issue, big issue, everything's flagged, well, almost everything's flagged. So when we see this number of red triangles, it usually means that there's an issue with the sample. So it's not necessarily a performance issue. Usually if it's a performance issue, it'll be some specific analytes, but when all the analytes are flagged as they are in this instance, then we can sort of go, okay, something went wrong with the sample and we need to look and see what it might be. So in this instance, the target score is not going to help us. So we want to look at our percentage deviation, and here you can see that the percentage deviations for each of the different analytes is fairly similar, -9, -9, -11. So in this instance, we can decide and we can ascertain that this has been a reconstitution error. So if all the percentage deviations are of a similar value and they're all below the mean or above the mean, then you know it's a reconstitution error. So in this instance, the lab have under-recovered for all the different analytes, so we can assess that this is a reconstitution error that the lab has made. So this is the other example. Stephen had mentioned that I would be showing you the two examples. So the previous one was a reconstitution error, and this is where the lab has submitted the results for the wrong sample. So in this instance, again, we have all the red triangles. So we know, again, this is likely to be a sample issue. So we want to look at our percentage deviations, and this time you can see that the deviations are all different. So we start off with -37, we'll go up to 255, on up to 329, and back down to -4.3. So when the percentage deviations show such a variability, then we can just assess that this has been the wrong sample. So either the lab have run the wrong sample and submitted the results for the sample they run, or they've submitted the results under the wrong sample number on the RIQAS net when they were entering the results. But it's the wrong sample has been assessed. So these results are not for the sample that's shown here. So in this instance, the lab can contact us to request that these results are removed, and therefore the running means won't be affected, and the end of cycle report, where we're looking at the averages of your performance indicators over the course of the cycle, wouldn't be affected. So again, the lab can complete the relevant paperwork to show that they have submitted the results for the wrong sample. These results would be removed, and the lab would see an R appearing instead of a sample number on their future reports, and then the running means will not be affected by this poor performance. So we're going to look at some of the other charts on the report and see how we can identify some different issues on the reports. So we have our report with all our different sections that Stephen has gone through, and we can see some differences here. So if we look at the Levy-Jennings chart, we can see that, I had fun drawing this line. We can see, so the performance decreases here, and then it goes back up, and then they run the negative bias for a little while, and then it goes back up again. So again, we can't look at any chart on its own. We need to look at all the charts in correlation with each other, because each one will give you a separate new piece of information, and it's important to interpret them all together. So this is the lab's Levy-Jennings chart with this funky little line showing how the performance has moved. But if we look at the percentage deviation by concentration chart, we can actually see that there is a different pattern. So at the higher concentration, the lab has very tight and very good performance. But at the lower concentrations, there's a much wider spread in the results that the lab are getting at these lower concentrations. So this is the area that they need to watch out for and look out for. So the results are all within acceptable limits. They're all within the 2 standard deviations here. But the lab just need to monitor then that lower concentration level and see if there's anything they want to do, whether they want to add another lower level control to try and improve the performance here. But this is why we can't look at any one chart on its own. We have to look at them all in together. So this is another example. There's not really any patterns going on here. The lab have a good spread of results above and below the mean. We have a black line down here on our report, which indicates the lab have made a change to their assay details. So it could be they've changed the method, or they've changed their instrument, or they have changed the reagent that they're using. So the black line will indicate any change to the assay details on a report. So Stephen earlier on had pointed out that the values across the top of the report are the means for comparison for the previous samples, and there's a little letter, the I and the M in front, which indicate the level of comparison. So here you can see that for the previous samples, the comparison has moved between the instrument mean for comparison and the method mean for comparison. So there are obviously more than 5 results for this and less than 5 results in the instrument, so the comparison has moved up. So maybe this is a new instrument that's come onto the market and we don't have enough labs running it, or we have enough labs registered, but they're not all returning for every sample. So we see this variability of moving between the different levels. So then when we look at our percentage deviation by concentration chart, you can see that although the lab have returned their 16 results on this chart, there aren't 16 results here. And that's because the results on this chart will only show results at the same level of comparison. So any sample across the top here that has an I, those are the results that we'll see reflected on this particular chart. And this means, so Stephen had showed how an instrument that has a bias would appear on the histogram. So if your instrument has a bias and there's less than 5 in your group, you'll end up being compared to the method mean, and you may find that for the samples where you run the method that you have a bias appearing here. So that will be reflected again on this chart depending on your level of comparison. But here in this instance again, you can see at the lower concentrations, when we're looking at the instrument comparison, that the lab again has a slightly wider spread at the lower concentrations than they do at the higher concentrations. So you can get a lot of information off the reports, but you need to, again, be using the charts in conjunction with each other and not alone. So here's another chart where this time you can see a pattern. So the lab's running with a positive bias, but the lab also have their results where they go up and then they come down and then they go up. And if you were looking at this, you could project that the results are going to go on up and you're going to end up being unacceptable for the next performance. But because we're covering multiple concentration levels with this, you can't just assume that this is the pattern of the lab's performance. You need to look at it in conjunction with the percentage deviation by concentration chart. And here you can see that there isn't a pattern. It doesn't matter at whether it's a low or high concentration. So we've got two outlier results. You can see here, and you can see these here and here on the concentration chart. But although we see this pattern on the Levy-Jennings chart, which if you were running IQC, you would see those trends and you would be monitoring those trends. So while we can see that as a trend on the report, because it's happening at different concentrations, it's not the actual trend that it might appear on the Levy-Jennings. That's again just to highlight across the top, we have the means for comparison. So again, you can see the differences for each of the samples. So we have 2 at 150 here, 1 at 269, and the next one that's at 300 is performing better than the one at 269. So you can see again here, if you look at these values across the top, that the performance that we're seeing here doesn't relate to the concentration of the samples being run. So with the percentage deviations and the running means, again, Stephen had pointed this out, that one outlier result, one per performer, can affect the running mean value. So back at the start of this chart, you can see the lab was performing well and the running mean is nice and close to the 0% deviation line. Then we have a high result and we have a low result, and we can see the shift. So we can see at the high result, the running mean goes up a bit, and then once we have this very low result, the running mean shifts back down and continues to run with a negative bias. But if you actually look at the lab's results, this is the same pattern we saw in the previous, this is the same lab's performance from before. You can see that the results are all running on the positive side of the mean. So if you just look at the running mean, you would think the lab have a negative bias, but if you actually look at the lab's results, the labs are actually running with a positive bias. So most of these results here are all within the acceptable limits, but if you looked at the running mean, you would get a different performance indication than the individual sample results, and it's because of this one result that is being included for the 10 samples it takes, that we're looking at the average of the running mean. So we can use the percentage deviation chart to establish if we have a bias at a particular concentration level, and we can also, as you can see in this instance, identify a possible systematic error with the instrument. So at the lower concentration level, the results are higher than the mean for comparison, and as the concentration increases, we can see there's a downward shift in the level of the difference between the mean for comparison and the lab's result. So here we can see at the lower concentrations we're measuring higher, and at the higher concentrations we have a more normal spread of results on either side of the mean for comparison. So again, the lab will need to look at this lower concentration and see if there's any action they want to take to address the fact that they have this positive bias at the lower concentration level. So we just want to demonstrate how, again, you might see different things when you look at the different reports. So this is from a blood gas report. So we have PO2 and we have glucose. And if you look at these reports, so we're just going to talk through each of these and see which one we think has maybe better performance. So for the PO2, we can see there are a couple of results that are sitting outside the acceptable limit, and it appears that the lab is running with a negative bias. So there's only one result here that's actually above the mean for comparison. For glucose, we have a wider spread of results. We have one outlier result, but in this instance, the lab has performance both above and below the mean for comparison. And this would be a more normal and preferred performance. We don't want to see this. This indicates the negative bias, and we don't want our performance to be running with positive or negative biases. We would want to see this spread of results on either side of the mean for comparison. So that's how this performance looks on the Levy-Jennings charts. So this is the same performance on the percentage deviation by concentration charts. So again, we have PO2 and we have glucose. So if we look at this chart and compare the two, this looks like this. So you can see the negative bias, but it looks like the lab results are much closer together. When you look at the glucose, you have a very wide spread of results. And so it would appear at first glance that the performance for PO2 is better than the performance for glucose. But as Stephen mentioned, you have to look at the scale of the charts. So for PO2, the scale for this percentage deviation chart goes from 0 to plus and minus 30, and for glucose goes from 0 to 8 and minus 8. So that would mean that this chart fits in this small section of this report. So actually the performance, while for glucose it appears to be much wider, because of the difference in the scale of these two charts, the performance for glucose is actually much better. All these results here in this area would be falling outside the performance that this lab has for glucose when we compare the two charts. So when we're looking at our percentage deviation charts, we always need to look out for this scale. It changes for each parameter, and it will change also based on the lab's performance for each sample, and the original scale will be based off the TDPA. So on the percentage deviation by sample chart, we have the red line that indicates our acceptable limits. So the scale on the two percentage deviation charts are the same, but we need to always look at the scale to see which is performing better, because the scale will change from parameter to parameter on the same sample report. So I'm going to hand back over to Stephen, who's going to take you through a few more troubleshooting slides.
Not really.
It's shaking his head at me, but
yeah. Hello again. Okay, yeah, so we're going to, thanks Sally for that, and some very useful information. I'm sure you can understand it, you can pull from the reports. So yeah, but what do we do then if we discover that we actually have a problem? So we touched on this earlier. So of course we want to investigate the source of the problem. So there's no point just determining that we have an issue. So what are we going to do with it? So this is where we want to implement some corrective actions, and of course then check the effectiveness of the corrective actions that we put into place. So let's go with this. But really what we want to determine is the root cause. So keep asking the questions why, just like as a young child would ask, well, why? And so you in the lab, as ourselves, we need to keep asking the question why. So why did it happen? What happened? Why did it happen? How can we prevent it from happening again? It is a team approach involving all this, not only from the technicians, quality manager, up to the lab director. We need to have a quality system in place that will not only be useful work for us to determine the errors in the first place, but obviously to reduce the errors in the long term. I use an analogy. I'll tell you it very quickly. Hopefully, this will be of some benefit to expand on this. But I've used in the past an analogy of coming out in the morning to get into your car to drive to work, and the car doesn't start. Okay, so we determine that the problem with that is that the battery is flat. So maybe that's the reason. Okay, so what's then a possibility here is we could, for example, okay, just get the battery replaced, and that could be the end of the story. But what happens then if a few days down the line we go out again and the same thing happens again? Because the battery is flat again. So the question is here, well, why did we ask the question why the battery was flat in the first place for the first time? It could be that the battery was flat because the alternator wasn't working. So the alternator wasn't charging the battery. So you ask the question, okay, so that's maybe not only then determining what the problem was, but determining what the root cause of the battery being flat. But in this case, well, you have to ask the question, is that the root cause? Is the root cause just that the alternator wasn't working? Or was it something else? So perhaps the alternator wasn't working because we didn't do the maintenance that we should have done on the car. So take this to a lab situation as well. So it's not only a case of determining the individual problem, but trying to determine what the root cause of that, and keep asking the question, well, why, and until you find out what the bottom line is. Very often it can come down to either maintenance, it can come down to staffing, maybe training. There's always a human impact in all of this, which we often find as we determine what the root cause is. But there is basically, really what you need to do is have a system in place that looks into this. So it's not just a simple question of finding out what the problem is, but yes, determining what the actual root cause. If we look for reasons for failures, this was a study that was done. It's quite old now. It's back from 1988. This was published, I think. And as we can see, the distribution for reasons for PT failures. Oh, sorry, there's four different studies. But as you can see, a lot of the cases comes down to the method. Could be technical, could be just simple clerical problems, could be with the actual survey itself, with the material from the survey. And a lot of cases, it can come down to unexplained. So this is one thing that we want to just emphasize at the moment here as well, in that if you do have a problem with an individual sample, is yes, okay, you want to try and look into it, but how much effort do you put into that determination? Because as we know, we can get random errors occurring for any individual sample measurement that we make. In general statistics, you'll have one result out of every 20, which will fall out of your normal distribution. So how much effort do you put into trying and determining what this root cause is? We certainly wouldn't make any sudden changes to our system based on a single result, because what we're looking for here, especially with EQA, is looking for long-term biases, or certainly well-established biases. You can't determine that you have a bias just based on an individual sample. So this is one of the reasons why we always say looking at running frequent samples and frequent analysis is important in EQA. because we can't make any proper judgment based on an individual result. We need to look at least multiple results, potentially over multiple concentration ranges, to ensure that we actually have a bias. Because what we certainly don't want to do is to introduce changes into the system that will actually have a detrimental impact. So unless you know what the root cause of the problem is, then you can't put proper corrective action into place. And if you actually introduce fudge factors or changes of your system without knowing what the actual root cause is, then what you're doing is actually you're introducing potential errors into your system. So two takeaway points here: don't make any major changes based on a single value, and certainly what you need to do is then try to determine what the actual root cause is before you make any substantial changes to your system. So whenever we monitor our EQA performance, really there is a flow chart. Now you won't be able to make this out actually on your screens. This is actually taken from our RIQAS Explain document. So certainly you can, it's available online, and you can look at it there. But really what we would say to you is to determine your own flow. So things that are, obviously each lab that is represented here this morning will have your own quality system in place. So you'll have your own determination of what a per result actually is. Some cases we're saying on our EQA reports that, okay, looking at 2 standard deviations. And that may be a trigger point for yourselves, but you may only look at maybe taking some form of corrective action if you have 2 results in a row outside 2 ESDs. You know, wherever you start looking at multi-rule sort of aspects. But this will be really determined by yourself. But certainly there is a flow chart of basically what you want to look at with regards to performance, really basically determination of per performance here. So certainly look at that in RIQAS Explained. It's quite a simple flow chart to go through. If you have any specific questions, I'd be more than happy to look at that separately. What we also would recommend is that for every individual sample, that instead of just looking at those results which are poor, is that you need to review basically everything, because you can have the starts of the developments of trends or sudden shifts in performance that are not necessarily falling outside of your limits, but may be the start of poor performance, or certainly a shift in performance. So, and to ensure that you go through everything properly, what we would sort of recommend is that you have a checklist similar to the one below, where you go through each individual aspect and that it's properly documented. I know the labs here in the UK that are accredited, you will have already something like this already in place. So really, whenever we're troubleshooting, we want to establish the following. So is the issue just me? Is it just my problem? Is it a problem with the sample? Or do we have a similar problem for other users using my instrument and reagent? Or once again, is there the start of something where I'm starting to show a difference from my peers, or there's a small group of us which are starting to move away from my peers? So let's look initially just to say, okay, let's see if it's just me that has the problem. Okay, so obviously the first question, do you see the same issue with your internal QC? How are we going to do that? Well, we want to make sure that we look for similar sort of conditions. So apples with apples. So look at it in terms of percentage deviation and not in terms of standard deviation, because standard deviation will be different between the EQA and the internal QC. So if we're going to do a comparison with your internal QC, do it in terms of percentage deviation. You're going to ask sort of some of these questions, just as we saw in this flow chart that we had, this checklist from the example, the page before. You're going to ask basically a list of questions. So when was the test last calibrated? Were there any significant changes made to the instrument or the reagents? Were any fudge factors applied? Are we trying to compare this result with a different system within the lab, which is different from how the other peers within your EQA report will be interpreting their reports? Once again, is any maintenance due or overdue? Because once again, do you have any shifts in performance either once that has occurred? Because sometimes the problems will occur after you've had maintenance, not necessarily just because it's overdue. But whenever you analyze, let's look specifically at your internal QC and gathering sort of the information. So if you're looking at it with us, really the sort of questions that we will want to know basically whenever we're trying to do this comparison is, okay, how often do you run your internal QC? Do you cover the same sort of concentrations as the EQA? Okay, we'll want to know basically the supplier of the internal QC, how the targets are set, whether they're fixed targets or you use a running mean, and basically how wide are the ranges compared to the EQA. Because very often we'll see that the comparison between the internal QC and the EQA, that the performance should match, and very often is the case that they do match. But because of the way the internal QC is set up, it's maybe not as noticeable. So do a like-for-like comparison, just as we said, do this in terms of percentage deviation. Okay, this is an example. I've used it before, but it's a perfect example for this sort of situation, where you say this lab came to us and said, my internal QC is perfect, but I have a constant negative bias on RIQAS. And certainly looking at it, they certainly do have a negative bias on the EQA report. Whenever we asked for their internal QC, they were using a target which was used from the internal sheet, so it was a fixed target. The mean that they achieved was very close to the target supplied. The CV was less than 0.5%. No result was ever outside the 1 SDE acceptable range. So you were to look at that, yes, you probably agree that the internal QC performance was good, if not certainly was acceptable, if not excellent. So let's look at it in a bit more detail. So whenever we looked at the two levels, the average deviation for the level 1 was minus 1.6%, and for level 2 was minus 1.49%. Now, when we plot that on the EQA report, here we go 1.6 and 1.49 for the two levels. So this is what the average internal QC level is like. And as you can see, actually, their EQA is actually performing very well. However, it is true that they are running with a negative bias. And also, as you can see, even whenever we go back to their internal QC, you can see that they're running with a slight negative bias. Now, it's not great in terms of magnitude, but it still is a constant bias that they're running with, which is more noticeable whenever you're looking at it in their EQA. So, okay, is this the case that you should have with your internal QC? And the answer to that is no, because your internal QC, you should be fluctuating around the target. And this is one of the problems that you have with using a target which is supplied by a manufacturer. You should, of course, be determining your own mean. You can certainly use the target mean as a starting point for your internal QC, but you should be determining what your own mean is and your own spread of results, and how you perform in relation to that. Because in this case here, you can see that the internal QC and the EQA matched basically, they matched very well, and they were running with a negative bias on both systems. Okay, so in this case, the larger internal QC acceptable range give a false perception of accuracy, and also then precision, because they were running with a negative bias, but because they were within their limits, they just merrily went on and thought everything's fine. Now, generally the performance was okay, but it was clear that they did have a negative bias. Okay, here we have another situation that came about very recently, actually. And this case was for total protein. And we had two different scenarios here. One, this is the total protein on our urine program, and then total protein on the CSF program. So the question was, okay, it's the same parameter that they're measuring. So the question is, why do they have such different performance? So the lab was, basically as we say, so why was it okay for CSF, but poor for the urine program? It came down very quickly. We once again went through the trying to help the lab to determine this, and it all basically came down to the calibrator that they were using, and basically they were using the wrong targets for the protein program, or sorry, for the urine, for proteins on the urine program. In this case here, they were actually using the CSF targets. So as you can see, there are two values, one specifically for CSF and one for urine, and they do have then different calibration values. And that's basically, they were using the one value for both. So instead of using the two, they were using the one. So this is why they showed the positive bias then for the urine program. So the labs were advised to calibrate each test separately, and there you go. Once they changed that, their performance improved then dramatically, as you can see in their latest report, latest sample. This sort of brings about some questions that we have as well, and we want to talk about classification and registering assay details correctly. A very high percentage of problems occur because labs are registered incorrectly. So we want to go through just a few examples here, just to bring out a few points. Obviously, whenever we go to register, or whenever a lab registered on the system, we tend to break the classification down by the method that the actual reagent uses. It can be then specific to the actual reagent, because sometimes we will have dedicated methods specific to a reagent type. It can be down to different calibrations and different standardizations. And because of this, because you can have one reagent supplier that provides multiple calibrations, multiple methods available, it can be confusing to register correctly. But if you don't do that, then obviously you're going to be compared to incorrect peer groups, which then will have a detriment to your performance indication. So if we look at this, this example for AST, this is another quite recent one that we came across, and this was from a Beckman folder kit. So for AST, So basically, the various methods that we have for this that the lab could pick from. So there were a couple of dedicated Beckman methods. There was a general colorimetric, there was a general tris buffer without the paradoxal 5-phosphate, the P5P. So whenever we were looking at this, the first one normally we look at is, okay, does it state the reagent or does it state the methods that the kit actually uses? So in this case here, there's no indication of the use of paradoxal 5-phosphate. So it also then, if we look at the methods, it's an enzymatic rate method. So we can very quickly determine that it's not colorimetric and it's not a tris buffer without P5P. There are dedicated Beckman methods, so it's more than likely to be one of those. So let's look at it in a bit more detail. So actually in this case here, it's actually, you can't determine what the method is just by looking at the insert sheet. What actually determines is actually in this case, or sorry, should I say, nowhere does it mention P5P, but I've already stated that. But nowhere does it, so that takes this one out. So nowhere then does it really refer to the actual standardization either. So really what we need to look at is the calibrator sheet. So in this case here, the Beckman, why we have those methods is because there are kits that do have P5P, but that's not the case in this situation. So depending on the actual kit in use, you can see that there are different standardizations. There are standards which are based on IFCC with the use of paradoxal 5-phosphate. And also then there's a method which is a Beckman, a calibration based on the Beckman master calibrator, which is modified without P5P. All confusing, I can hear you say. But this is part of the problem, because sometimes it is hard to determine how you should be classified. But in this case, so it's not necessarily, what we're trying to emphasize here is it's not necessarily easy just to tell from the kit insert. Sometimes you have to look specifically then, where we have multiple methods and where we have methods that relate to calibrators, that then would be an indication that you need to look at your calibration sheet to see what actual calibrator value that you're actually using. Why we have different situations in this case is that sometimes, because we're a global scheme, we have reagent manufacturers have different calibrators in different parts of the globe. So in this case, mainly in South America, there's the use of a different calibrator traceability, and this is where we have these coming through. So there's a different, same calibrator, same lot of calibrator, but there's different traceability provided depending on where you are in the world. So this is once again one of the reasons why you'll see some of these things coming up on our classifications. So the way it worked out in this one was a Beckman modified IFCC reference without P5P. So this is how the lab should be registered. If there's any confusion with how you should be registered, please contact us and we'll be more than willing to help to try and classify you correctly. Because really without correct classification, first of all, once again, it's going to be not only difficult for yourselves to have proper report interpretation, but also, of course, then because you're in the wrong grouping, then you will potentially have an impact on results in somebody else's group. So this is one of the reasons, of course, why we have exclusions as well, because sometimes labs will classify themselves incorrectly. A second situation here then is with AST. Once again, this is where you have this is Roche in this case, but where you have basically the use of the same kit, but where you can use it for two different purposes. In this case, where we have once again, the paradoxical 5-phosphate, or where you have with and without activation. Okay, so in this case here, the kit itself is the same, but it's how you use the kit is different, and there's different ACN numbers, just depending on whether you're going to use it with or without paradoxical 5-phosphates. So the ACN, for those of you who don't know, is your application code number. Same kit, different application, which is very often the case. And we often get asked the question then is, well, why can we not, whenever we register somebody, why can we not simply, you know that we're using a Roche system, you know that we're using this kit, why can we not, as in RIQAS, cannot register yourselves correctly or in the first place? And this is sort of the situation, because very often you can use the same kit, but with different applications or with different standardizations, different calibrators. So this is why we can't do it directly, but we're more than willing to help to do that, to assist you in that process. Okay, so there you go. This is a different, example, but something similar, as I say, different standardizations. So in this case here, it's the same kit, but using two different standardizations. One's using IDMS, and the other one's Able Candle. So same sort of situation we've just mentioned. In this case, for Beckman, once again, cholesterol, you can see then here that you have to look at the calibrator insert to find the standardization. It doesn't actually mention it's actually within the insert itself. So once again, going to the system calibrator, once again, let's go to IDMS and Able Candle, similar to the example we just looked at.